Another periodic trend is ionization energy. Ionization energy, abbreviated IE, is the amount of energy needed to remove an electron from an atom in the gas phase. It is taking an electron away. The result is a cation with an overall positive charge. We can write an equation that represents the reaction. For example, this one for the ionization energy of sodium. The neutral sodium atom is what we are starting with on the left of the arrow. On the right of the arrow, we end up with a sodium ion, which has lost an electron, and separately, that unbound electron. The energy for that reaction is a positive 496 kilojoules per mole. That means 496 kilojoules of energy must be added to sodium in the gas phase to make it lose an electron. The overall trend for ionization energy is opposite compared to atomic radius. The largest values for ionization energy are towards the upper right of the periodic table. For example, helium has an ionization energy of 2,370 kilojoules per mole. It is very difficult to remove an electron from helium. The smallest values are toward the lower left of the periodic table. For example, cesium has an ionization energy of 380 kilojoules per mole. It still takes energy to remove an electron, but not nearly as much. Again, the overall trend is made up of two individual trends, one going across a period and one going down a group. The reasons for the trends will actually be the same as the reasons for atomic radius, though in terms of numbers, the trends are opposite. Going across a row on the periodic table, effective nuclear charge increases. Because electrons in atoms towards the right of the periodic table feel more positive charge, they are pulled inwards by the atom more, and therefore it will take more energy to pull them away. It is like there is a tug of war going on, and the atoms on the right of the periodic table are able to hold onto the electrons better because they have more protons to do it with. Going down a group on the periodic table, ionization energy decreases. As there are more and more energy levels, like layers of the onion or Russian stacking dolls, the electrons on the outside of the atom are farther away from the nucleus that is hanging onto them, so they are able to be pulled away more easily. We do see some notable exceptions to the overall trend that ionization energy increases going across a row on the periodic table. Going from 2A to 3A and going from 5A to 6A, there are dips in ionization energy, even though there is an increase in effective nuclear charge. Going from 2A to 3A, there is a decrease in ionization energy that is due to the type of orbital the electron to be removed is in. The outermost electron in beryllium is in a 2s orbital, whereas the electron being removed from boron is in a 2p orbital. Since the 2p orbital is higher in energy than 2s, electrons are easier to be removed from it. It's kind of like pulling someone off of a chair versus pulling on them while they are standing on the floor. The one that's higher is less stable. So even though boron has a higher effective nuclear charge, it's easier to remove an electron from boron than from beryllium, due to the subshell the electron is coming out of being higher in energy. The other exception is going from 5A to 6A. This time the outermost electrons are both in p orbitals, so that can't be the reason for the dip. Instead, it has to do with pairing energy. All else being equal, electrons would rather not be paired. The electron to be removed from nitrogen is relatively happy by itself, but the electron to be removed from oxygen is a little bit unhappy in its living situation and is therefore a little bit more happy to leave. Therefore, there's a dip in ionization energy going from nitrogen to oxygen. It's easier for oxygen to lose an electron due to pairing energy. We are not limited to just removing one electron. We could remove a second one or a third one, or even more. The energy required to remove the first electron would be IE1. The energy required to remove the second electron would be IE2. If you were starting with a neutral atom and wanted to find how much energy was needed to remove 2 electrons, you would add the IE1 and the IE2 together. Each ionization costs more energy than the one before it. For example, the IE1 for sodium is only 496 kilojoules per mole. The IE2, which turns the sodium plus 1 ion into the sodium plus 2 ion, costs 4,562 kilojoules per mole. This chart shows the ionization energies for elements 3 through 11. For any given element, IE1 is the smallest value, and then IE2 is larger, and then IE3 is even larger than that, and so on. The reason why it takes more energy to remove more electrons is you would be trying to remove them from something that is already positively charged. The more electrons have already been removed, the more positively charged the ion will be, and it will therefore take more energy to take another one away. We also notice on this chart that each element has a huge jump in ionization energy values as it transitions from valence electrons being removed to having core electrons removed. For example, beryllium has 2 valence electrons. IE1 and IE2 are removing those valence electrons. IE3 is much larger because it is removing an electron from the previous energy level, which is closer to the nucleus and therefore feels more attractive forces. Boron has 3 valence electrons. IE1, IE2, and IE3 are removing those valence electrons. IE4 is where the big jump happens for boron, because the 4th electron to be removed is a core electron. Arrange the elements magnesium, chlorine, phosphorus, and rubidium in order of increasing first ionization energy, IE1. Is it A, chlorine, then phosphorus, then rubidium, then magnesium? B, magnesium, then phosphorus, then rubidium, then chlorine? C, chlorine, then phosphorus, then magnesium, then rubidium? Or D, rubidium, then magnesium, then phosphorus, then chlorine? The correct answer is D, rubidium, then magnesium, then phosphorus, then chlorine. For first ionization energy, we can just follow the trend that the largest values are towards the upper right of the periodic table, and the lowest values are towards the lower left of the periodic table. We would not be able to follow such a trend for IE2, IE3, etc., because of the large increases from valence to core electrons. We can walk our way along the periodic table for our answer. The lowest value would be at the lower left of the periodic table, which would be rubidium in this problem. We go up and right to get to magnesium, then right to get to phosphorus, then right to get to chlorine. Which electron is hardest to remove from an atom having 4 valence electrons? Is it A, first to be removed, B, second to be removed, C, third to be removed, or D, fourth to be removed? The answer is D, fourth to be removed. It actually doesn't matter how many valence electrons the atom has for answering this problem. Each subsequent removal will always be harder than the previous one. IE4 is larger than IE3, which is larger than IE2, which is larger than IE1.